All right, this is it, the moment we've all been waiting for. Not that, I mean, I don't know. This whole thing's been great. Lawrence Krauss is an American theoretical physicist who is a professor of physics, foundation professor of the School of Earth and Space Exploration, and director of the Origins Project at Arizona State University. One of the first talks that Kath and I saw at any kind of an event, any kind of an atheist convention, was in Burbank in 2009 where Lawrence spoke. And I think it was the first time you did the universe talk, maybe.
Well, that version.
Yeah, that version. And I mean, it blew us away. That is what created the impetus to start a group here. That's what created the impetus to do this kind of an event. And I'm just so grateful to Lawrence that he agreed to come. And it wasn't easy. He had to, I think you've been flying for, 30 days straight or something, pretty much. So I want to thank you so much for coming. Ladies and gentlemen, please join me in welcoming Lawrence Krauss.
Thank you. Thank you. Thank you very much. So, thank you. Thank you, Bill. It's a pleasure to be here. And you've done a wonderful job, and it's an honor to be here. And I appreciate all of you staying. I thought most of you would be on planes by now, in which case we could have just gone for a cup of coffee. But anyway, it was a privilege to speak after Miriam and the important message that she gave, which is really important. One of the nice things about cosmology is it doesn't matter. And so it's good to take you away from the problems of the real world and the urgent problems that she talked about that I thought she did such a wonderful job talking about. I also will try not to make any fun of philosophers today. My reason for that is that I attend a little bit of the debate, and those two guys represented themselves as philosophers, so I think they made enough of a joke of the whole thing anyway without me doing that. I'm also acutely aware and honored that many of you have watched me in one form or another on YouTube or on TV or in fact in lectures I recently gave in both Vancouver and Calgary this year at different times. So I was feeling pretty badly about coming to talk on this subject, and I didn't want to give. I never like to give the same talk anyway. But so there'll be overlap with the talks I've given, but it won't be the same in any way, and I want to emphasize different things. So for some of you who wanted to come and get the whole thing from scratch, I'm sorry, but I thought I'd touch on some different topics just out of deference to the people who drove many hours and may have seen me somewhere else. And anyway, but nevertheless, most of it will be there. But I do want to make this unique and focus on some things, also because of as I'll indicate, because of the specific time. Oops, here we go. I'd rather just listen to Monty Pythons all day, but anyway. I'm very upset about the fact that I played that song. I was honored to be asked to give the opening or keynote talk at a memorial service for my friend Christopher Hitchens in New York. And I've seen it on YouTube, but they took out the Monty Python's music, which really upset me. Anyway, my reason for giving that talk, which at Burbank, which I guess inspired Bill in some way, was the same reason I talk about everything. It's really not so much to attack ignorance as to inspire people not to be ignorant. And one of the ways to do that, it seems to me, is to point out the remarkably amazing aspects of our universe, which I'll try and talk a little bit about, and really treat the idea of the universe as a mystery, because mysteries are what drive us forward. It's not the knowing things, it's the searching for things that makes life worthwhile, in my opinion. And so I will be guided, as I try to be, by the real universe. And this is a picture of the real universe as seen from a place other than where I used to live. As many of you heard me say, in Cleveland, I used to always have to introduce lectures by showing people stars and saying, these are stars. But in Arizona, I don't have to anymore. And here, I noticed it was clear at least a few nights. But the question that I've been trying to answer, or at least address, and which lately has caused so much controversy that surprised even me, among people I didn't expect to hear from, is the question, why is there something rather than nothing? And the reason that's an important question to address is that it's normally framed as a religious question and a theological question or a philosophical question. Something that is beyond the domain of science. And what is fantastic, it seems to me, is that science has progressed in the last 40 years or so, my field of science at least, to the point where that question and several other questions, which we never thought would be addressable by science, are at least addressable. We may not have answered all of them, and I want to make that clear, as I've tried to do. But we have led ourselves to a plausible resolution of how a universe could come from nothing by natural laws without any supernatural shenanigans. And just the fact that that's plausible is worth celebrating. But in the process, as always, science changes the way we think. That's what's good about science, because we change our minds, unlike religion. And one of the ways we've changed that is changing what we mean by these very words, as I'll talk about. So I want to move from what is obviously the traditional answer that was given for many centuries is just this answer, which doesn't tell you anything. You're in the beginning, and then you write a book that doesn't tell you anything. So what is really important is not being guided by what the story we want to tell, but the story that the universe tells us, and that's the story I want to tell. The story that we're driven to by this remarkable universe, the surface of which you just scratch when we take pictures like this. Because as beautiful, this is a globular cluster in our galaxy, but as beautiful as that is, it is just the tip of a cosmic iceberg. We have realized that the really important stuff in the universe is not the stuff we can see, but the stuff we can't see. That's changed our picture of everything from the beginning to the end, as I'll discuss at some length. Now, as I say, I want to jump in here and not go through some of the introductions I've done before. I just want to say that the picture of our universe changed completely when Albert Einstein discovered, theoretically, that the universe was describable and gravity was describable by a remarkable fact, the fact that space and time are dynamical. They're not fixed. They can respond to the presence of matter and energy. They can expand, they can contract, they can curve. And that changed everything, because it really gave us the first picture of space and time themselves, and therefore the first picture of the universe. It was really the first theory that allowed us to describe the universe, because it was a theory not just of how objects move through space, but how space itself evolves. And the universe became dynamical. And the important question that arose after we discovered the universe was expanding, and again, as I say, I apologize to those of you who I'm not giving the opportunity to hear how we did that, but you can read the book. The important question was what kind of universe we live in, because it looked like the future of the universe was determined by geometry once we discovered that the universe can be curved. And a three-dimensional space could exist in one of three different kinds of geometries, so-called open, closed, or flat. That's it. That's a complete description of the geometry of three-dimensional space. It also was the complete description of the geometry of two-dimensional space, and that's what these images are here for, but they shouldn't confuse you. And I think if I wrote the book again, in fact, in the paperback, I'm probably going to rewrite a page or two, because I still think I confuse people about what a flat universe means. So here are two-dimensional pictures of two-dimensional universes, because I can draw two-dimensional universes. I can't draw curved three-dimensional universes. I can't even picture them very well. I can picture them mathematically, but not intuitively, because I'm stuck in three dimensions. I'm stuck in the universe in which we live, as all of you are, and as none of the Republican candidates in my country are. But because of that, it's hard to picture. But we can draw them, and it's nice to see them here. A flat universe, like a flat piece of paper. The surface of a sphere is a closed two-dimensional surface, and the surface of an infinite saddle is an open two-dimensional surface. Now, as I say, in three dimensions it's more complicated, but a three-dimensional flat universe is just the universe you always thought you lived in, and this is what I would write in the book now, I think, if I had a chance. It's just the universe that you've always felt you always lived in. It's a universe in which light travels in straight lines, and the three axes, X, Y, and Z, in deference to Canada, the X, Y, and Z axes always remain in the same direction. In a curved universe, those axes in one place point in a different direction than they do in another place. That's it. So a flat universe is just a simple universe you thought you lived in. It's not flat like a pancake. It's just 3 dimensions as you always thought they were. Now, all of that sounds very nice, and it's wonderful to use at bars. But the real important stuff is that in the case of a universe dominated by matter, the kind of universe we lived in determines the future. In a universe dominated by matter that's expanding now, if it's open, it will go on expanding forever. In a closed universe, it will expand and reach a maximum point and then stop, and then return to a big crunch, the reverse of the Big Bang. And a flat universe is the boundary between these two. It's a universe that expands forever and slows down and never quite stops. Now, this was the picture we always told people, and I've written about this in books, in old books of mine. And it was the picture that inspired me to go into cosmology, or at least spend part of my time doing cosmology. I'm by training a particle physicist, and I got into cosmology because I realized I thought I might be able to be the first person to know how the universe would end, which seemed like a good idea at the time. And because once I determined which universe we lived in by the geometry, I would know the future. And you'll see why particle physics determines, we thought, the geometry of the universe. So, the question, that the holy grail of 20th century physics became, which universe do we live in? That became the mission after we discovered the universe was expanding in 1929. And we spent 80 years or so trying to determine which universe we live in, and we now know the answer. And we know it by weighing the universe. Because to determine the geometry of the universe, since space is determined by the presence of matter and energy, we have to determine how much matter and energy there is in order to determine the geometry of the universe. And so I'll just give you, I will show you how we've weighed the universe and how we've determined also the geometry of the universe. And I do want to show you one thing which some of you, certainly who at least have watched YouTube, haven't seen. Because it gives you a sense of how much science has changed in the last... I'm a big fan of history, and I want to take you back to a kindler, gentler time. Well, it wasn't that kind in the world, but it was kind in science. 1936, and this is the journal Science, which is still a somewhat distinguished scientific journal. And in that journal appeared a paper called Lens-like Action of a Star by the Deviation of Light in a Gravitational Field. Sounds kind of tedious, but I want to show you how it began, especially for there's some young people here, and I'm really talking to young people in general, I hope, because I want to show you how things have changed a little bit, and some of you maybe are in university, are going to go into, and may one day submit a paper to Science Magazine, and one day be rejected. So this paper began some time ago. R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Now you try and do that today, okay? Try it. It won't last very long. It's just as a different time. Now the author had some credentials. The author was Albert Einstein, so maybe that'll help him along a little bit. But what he was talking about in this paper was a calculation that he thought was entirely unimportant. And it was useless, in fact, in his mind. And it was the simple result. He'd already shown that light curves in a gravitational field. But that meant if you had a mass here, a large enough mass distribution, and a source of light behind it, the light rays from that source could go around and both curve around that mass distribution and converge again. And that would magnify the image. That would mean gravity can act like a lens. A star can act like a lens. And similarly, like a cut glass goblet, which has many jagged edges, if you have a mass distribution that's irregular and you pass the light rays around it can produce many images. If I look through a cut glass goblet, I'd see many different images of you. So space can act like a lens. It's an interesting observation, but Einstein said it was so unimportant it would never be observed because he was largely illiterate about astronomy. This is the calculation he did in 1936 in his notebook. It's not a complex calculation. But the point is, he thought it was so unimportant that he'd forgotten. If you go to his notebooks in 1912, you can find exactly the same calculation. He did it in 1912. He just forgot he did it because it said it would never be important, never be. And in fact, one of my favorite parts of this little history of science is the letter he wrote to the editor of Nature afterwards, or Science afterwards, where he said, "Let me also thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." So that's how science is done, okay? In any case, he was wrong. It wasn't of little value. It allows us to weigh the universe. And this picture is the phenomena that Einstein said would never be observed. It's a Hubble Space Telescope picture. And it's one of the things that provides and should provide us all inspiration, and those of people in this room who may like the word spiritual, it should provide you some spiritual something. It's a picture of a cluster of galaxies. The really amazing thing about this picture is that every point in this picture is a galaxy, not a star. And this cluster of galaxies is a conglomeration of galaxies. Almost all galaxies live in clusters. They're the biggest bound objects in the universe, about 10 million light years across, this picture. But this cluster is 5 billion light years away. Okay? That means the light left these stars before our Earth and Sun formed. The Earth and Sun are about 4.5 billion years old. So the light left before the Earth was even around to capture the light, 5 billion years later. And the other thing is that each of these galaxies contains hundreds of billions of stars, 5 billion years ago. So, and if there are stars like our sun, then most of them have burned out. So you can imagine there are civilizations living on those galaxies, in those around those stars that are long gone. We'll never know about them. And there could be thousands of them in this image. We don't know. It's really kind of, to me, I find that inspirational, that aspect. Every time I look at a picture like this, it causes me to think about things like that I would never think about otherwise. That's why we need to keep looking at the universe, because it inspires us in a way that obviously myth and superstition don't. But in any case, this bound cluster there's some obvious, you don't have to be a rocket scientist to see that there are images here that are different than the others. They're blue things. Those blue things look different than the other galaxies. And what those blue things are multiple images of a single galaxy located 5 billion light years behind the cluster, 10 billion light years away from us. And we wouldn't even see that galaxy except for the fact that the space has magnified it and distorted it. Each of these is a different image of the same object. It's distorted it and produced multiple images just like that cut glass goblet. It's amazing proof that space is curved around objects, that space can act like a lens. So it's validation of that very fact that Einstein said would never be observable. But the important thing about science is that what is first a signal becomes background. And it's amazing verification, but we actually understand general relativity. We don't need the verification. We can now use it for something else. And we can use it because we understand how mass curves space, and therefore we can use this image and ask how much mass is there in this system. We can weigh the system because we can ask where would the mass have to be distributed and how much of it would there have to be to produce precisely the image you see. It's a very complicated mathematical inversion, but you can do it. And the first people to do it were Tony Tyson and colleagues at Bell Labs a while ago. This is the inversion. So this is a picture of where the mass is in that cluster of galaxies. And you can see the spikes are where the galaxies are. But the really important thing is that most of the mass, this huge mountain of mass, is where the galaxies aren't. There's 40 times as much mass in this image as meets the eye. In fact, around each galaxy, there's more mass than meets the eye. Most of the mass of the system is not the very spike where the visible mass is, but these halos around it. 40 times as much mass as shines. And as I say, physicists are very creative. We call that dark matter. And the remarkable thing, the things that makes it very exciting and inspirational to some of us, and really the reason I got in the field, in fact, is that there's so much of this dark matter that we can say with virtual certainty that it can't be made of the same stuff as you and me. We know how many protons and neutrons are in the universe. It's a triumph of cosmology, which I won't talk about today, and maybe in the question period if there's one. But we know how many of them there are, because we can test that idea, not because we know, because by revelation, but we know because we can test the idea. And there's 10 times too much stuff here to be accounted for by protons and neutrons, which make you and everything in this room up. And that means that this dark matter, we're virtually certain, is some new type of elementary particle, which makes it very exciting because it's not just in that galaxy or in that cluster. It's, of course, in our galaxy, in our cluster, and it's not just out there. It's in this room, going right through you now. And that means we can do experiments here in this room to look for dark matter. We wouldn't do it in this room because we're above ground, and we're bombarded by cosmic rays all the time. So we build experiments underground because the cosmic rays get shielded. But this dark matter, we think, interacts so weakly, that's why it doesn't emit light, that most of it goes right through the Earth without knowing it was there. But we can build experiments which can be very sensitive. Most of the dark matter particles go right through the Earth as if they didn't know it was there, but some of them will stop. In fact, one of the things I'm proud of, I suppose, is that I proposed the experiments 25 years ago that are now being used to look for dark matter. Here's such an experiment. It's really quite simple. Well, it's simple for me to talk about it. It's not simple to do it. But this is a boule of germanium, the same stuff that makes up your computer chips. And if you cool it down to about 1/1000th of a degree above absolute zero, which you can do easily enough, then most of the dark matter particles will go right through the Earth without knowing it was there, but every now and then one of them will bounce off, simply bounce off a nucleus of germanium, heating the whole thing up by 1/1000th of a degree or so. And it's amazing. I mean, the hard part is that the event rate you expect in a detector like this is maybe one event per every 10 years. And you're looking for a change in temperature by 1/1000th of a degree, or an energy deposit of, well, the units that don't really matter, that's very small. So you're looking for very small energy deposits very rarely, and then you have to worry about radioactivity, and it's a real triumph that experimentalists can even do this. But they have done it, and there are experiments like this being built all around the world. Some are going to be done in Sudbury, where there's a deep mine, and other places. No one, well, except for a group in Italy that's wrong, no one's actually seen anything. But we may one day know what the dark matter is, what the identity of the dark matter is by experiments like this. And the other thing that makes it even more exciting and timely, perhaps, is that we don't have, these dark matter particles, by the way, were created at the beginning of time. Were created in the early universe. If we detect them, we'll get a signature in some ways of what the universe looked like. It's something like a millionth of a billionth of a second old. But we don't have to just wait for that necessarily, because we can create them. We can try and create conditions that are similar to those when the universe was a millionth of a billionth of a second old. And there are places on Earth where we have those kind of conditions, most notably now outside Geneva at the Large Hadron Collider, where we, for brief times and very small scales, create those conditions, and haven't created a black hole that will destroy the world, I'm happy to say. But we create those conditions, and therefore we might actually create these particles. So it's a race right now between the people who have detectors like this underground and the people at the Large Hadron Collider to see who can discover the nature of dark matter and discover what particle it is. And then we'll know the dominant stuff in the universe. Because, as this is clear, we are not the dominant stuff in the universe. A lesson I'll keep repeating over and over again. We, and you in particular, not me so much, but you in particular, are insignificant. Anyway, more insignificant than we ever imagined. And so much for a universe made for us, as I point out. Okay, but we don't have to know what it is. We just have to know for the moment to determine the future how much of it there is. So we go back to this picture, and this picture has allowed us to weigh the universe, because anything that could fall into anything will fall into a cluster of galaxies. And so if we can measure clusters, we can weigh the universe, and we have finally done so, and this is the answer right there, and there's people fainting in the back, I see. This is, when physicists have an important number, they give it a Greek letter to sound scholarly. And this number, is omega, is the ratio of the total amount of stuff there is in the actual universe divided by the amount you'd need to make an exactly flat universe. And if omega is 1, the universe is flat. If omega is bigger than 1, the universe is open. If omega is less than 1, the universe if omega is bigger than 1, the universe is closed. If it's less than 1, the universe is open. And so what we seem to have discovered with 95% certainty, in fact far more than 95% certainty, because you'd have to be many more than 0.1 away to get to 1, that the universe unambiguously appears to be open. We seem to have answered that holy grail which got me into cosmology. The universe is open, and therefore, if it's dominated by matter, it will expand forever. Is what? Open is the saddle for two-dimensional. Okay. The paper is the flat universe. Okay. So, but there's a problem, and that is we thought we lived on the paper. Okay. In fact, as I point out, we knew we did. We theorists knew that we lived in a flat universe. We always know the answer. We're not often right, but we always know the answer. And the flat universe is the only mathematically beautiful universe, so we were convinced we lived in it. I'll show you another reason why we're In fact, more relevant to this discussion, why we were pretty certain we lived in a flat universe. But here these damn, and I can use that word here, these damn observers kept coming up with the wrong answer, as they always do. And so we were concerned. Well, it turned out this is, of course, obviously a flawed way of determining the geometry of the universe, because you're weighing the universe, you're plugging into Einstein's equations, you're comparing it to the expansion rate, and you're looking at things, and then at the end, you work out what the curvature of the universe is. It would be much better to measure the curvature of the universe directly. And that we have been able to do in the last 15 years, amazingly. Amazingly to me in particular, because I was amazed when they did it, but then I was even more amazed, maybe like Einstein, discovered I'd actually published a paper 10 years earlier about it. I'd totally forgotten, because I didn't think it would ever be observable. But we have measured the curvature of the universe, and I just want to show you the result. I'm not going to give you all the preamble here, because I want to get to some other stuff. The result is the following. We've used the most important observable in cosmology, the cosmic microwave background radiation, the afterglow of the Big Bang, that gives us a baby picture of the universe. When the universe was 100,000 years old, it was opaque. We can't see past that point. But then it became neutral. Matter became neutral because the temperature of the universe at that time was about 3,000 degrees. The universe was a plasma, and it was opaque. But as it cooled down below that temperature, protons captured electrons, matter became neutral, and neutral matter is transparent to radiation, basically. And so when we look out, we can look out as far as we can look in the universe until we get to that point, just like I can look out as far as I can until I get to this wall. The wall's opaque. And so if I look out, if there's a prediction there was a Big Bang, if I look out far enough, I should see radiation coming at me from all directions from that moment when the universe became transparent. And the universe was 3,000 degrees then, but it's cooled now. It's about 3 degrees. And that radiation was discovered by accident in New Jersey, of all places, by two people who didn't know what the hell they were doing. But it's okay. They won the Nobel Prize anyway, because you don't have to know what you're doing to win the Nobel Prize. It's a clear. You don't really. You just have to discover something. And they discovered this radiation, and it changed our. It was one of the fundamental bits of evidence that told us the Big Bang really happened. Now we can take a picture now of that radiation. That picture, by the way, has won another Nobel Prize because it's a baby picture of the universe. And here is one of the first experiments to take a picture on the scale that was necessary. This is the boomerang experiment in Antarctica. It's a balloon and a microwave receiver, and this radiation is now in the microwave band. It was sent way above the Earth's surface, away from the heat of the Earth, and went around the world, which of course is easy to do in Antarctica. In the South Pole, you just do this. But there, it was at the edge of Antarctica, and it took an image of this radiation. And what's really important in this picture is looking for these hot spots and cold spots. These, by the way, are the primordial lumps created at the beginning of time by mechanisms I'll talk about in a second that people don't normally get to hear about, but you will. That tell us, by the way, we're all here due to quantum mechanics. It's really amazing. And we don't celebrate it enough, it seems to me. But they were created in the very first instant of the Big Bang, and they would later collapse to form all the galaxy clusters and galaxies and stars and planets and aliens and everything. These were the primordial little lumps that would later collapse to all the structure that you saw in that later picture. And it's really amazing that we can look back 13.7 billion years to look at that image of that baby picture. But the important thing is the size of these. Because we know the physical size of these lumps is about 100,000 light years across, because those are the biggest lumps that could have collapsed at the moment the universe was 100,000 years old, because no information travels faster than light. And so to collapse, you have to know that you're a lump. And to know you're a lump, you have to have light be able to travel across you. So these are 100,000 light years across, but how big do they look? And that's the point, because just like in those images I showed you before, in a universe where light doesn't travel in straight lines, if you have a ruler that's 100,000 light years across, if the light travels in straight lines, we would expect the lumps to be about 1 degree across. But in an open universe, it turns out the light rays diverge as you go back in time, and the same ruler will look smaller, maybe half a degree. And in a closed universe, the light rays converge as you go back in time, and so the same ruler will look bigger. So really, it's just causality. Tells you just look at these lumps and say, how big are they? And that tells us directly the geometry of the universe. It's amazing. And so to compare this image with various universes, this is a different false color image of the same picture. We can create universes on a computer, closed, open, flat, in this case three-dimensional, and then generate lumps of 100,000 light years across at random, and ask what it would look like. And in a closed universe, the lumps would look this big, but these are bigger than these lumps. And in an open universe, the lumps would look this big. The same physical size, but they look that big. These are smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. We now know to an accuracy of 1% or so that the universe is flat. In fact, this is a mathematical way of presenting the same picture that I don't normally show. But the prediction, the curves for a flat universe, and the data are the points. Unbelievably, perhaps, the universe is flat. So we can pat ourselves on the back. Theorists. Of course, we can't pat ourselves on the back because, we missed something, right? I just proved to you, I hope, that the universe was open. Well, I thought it was open because I added up all the mass in the universe, ended up to 30% of what you needed to make a flat universe, but the universe is flat. We're missing 70%. Okay? So that's a problem. But before we do, I just want to mention this other aspect. This image, the data agrees with the observations, or the theory agrees with the observations, really beautifully, not just because the universe is flat, but this is because these lumps, and this is called a power spectrum, the statistics of these lumps is precisely that which would be expected if quantum mechanics in the early universe, which produces quantum fluctuations, quantum mechanics says everywhere things are fluctuating on very small scales. If those very small scale fluctuations as the universe got puffed up, got frozen in, and became real density fluctuations, they would produce precisely what we see today. If that's true, then you are here literally due to quantum mechanics. You are quantum children. I've talked about star children a lot in other cases, but you're quantum children too. So I suppose if I wanted to produce another YouTube video or something that someone would record, I could say, forget Jesus, quantum mechanics happened, so you'd be here. Okay? But I find that amazing, that the quantum mechanics, the physics of the very small, could be responsible for everything we see. In any case, to get back to the matter at hand, we're missing 70% of the universe. Okay. Where could it be? Well, it turns out, if you put as I've often said, gravity sucks. You all know that who took physics. Everyone here knows gravity always sucks. It always pulls, it never pushes. That's not quite true. All normal types of gravity always pull. But if we put energy, instead of into matter or radiation, into empty space, and by that I mean you take a region of space and you get rid of all the particles, all the radiation, so there's absolutely nothing there. And I mean it, there's absolutely nothing there. If that space weighs something, it'll actually be gravitationally repulsive. Now, of course, it's absurd that empty space should weigh anything, but if it did, it would be gravitationally repulsive. And then when we look at the expansion of the universe over time, if it was dominated by the energy of empty space, actually, the expansion of the universe would speed up and not slow down. Now, in 1998, two groups of astronomers who didn't know what the hell they were doing decided to measure the rate at which the universe was slowing down. And actually, I think I'll just, hold on, I'm going to come back. I actually departed from what I thought I'd do. Okay, good. Forget the ignorant astronomers for the moment. We'll get back to them. I felt you would be so incredulous about the fact that empty space would have energy that I better talk about this a little bit. So, it is insane to think that empty space can have energy. It is illogical. It doesn't make sense. It violates common sense. And the point I often try and make, especially to Christian apologists, is that science doesn't have to respect our common sense. The universe is the way it is whether we like it or not. And if it doesn't respect our common sense, that's a problem with our common sense. Okay? And that's probably the hardest thing to convince people of. Okay? And it turns out that the reason it doesn't respect common sense is that small scales, the universe is governed by relativity and quantum mechanics, two aspects of physics that don't make sense, at least common sense. And when you put them together, it's even worse. And when you put quantum mechanics and relativity together, you find out at the smallest scales, empty space is not really, well, it has no particles in it, but it's really much more interesting. It's a boiling, bubbling brew of virtual particles popping in and out of existence in a time scale so short you can't measure them. This is actually not just an animation. It is the result of a mathematical calculation of what the space inside of a proton looks like. These are particles and fields that are popping in and out of existence in a time scale so short we can't measure them. Now that sounds like philosophy, and I won't make any statements about philosophy. But it sounds like, it sounds like theology. It sounds like counting angels on the head of a pin. But it isn't. Because these virtual particles, as they're called, while we can't detect them directly, we can detect them indirectly. So they're science. And in fact, one of the greatest calculations in the last part of the 20th century was to be able to calculate the effect of these particles on a proton. You may have learned, if you've gone to a good high school or a good university, that protons are made of quarks. These particles are called quarks, 3 quarks. Well, that's fine, but in fact, if you add up the mass of the quarks inside a proton, what they don't tell you in school is if you add up the mass of the quarks inside of a proton, they account for 10% of the mass of the proton. 90% of the mass of the proton comes from these virtual particles popping in and out of existence. So they have indirect effects which we can determine, and if we don't include them, we get the wrong answer, and if we do include them, we get the right answer. In this case, just to a factor of 10% or so, but in the case of the energy level spacings of atoms, to better than 1 part in a billion. The best predictions in all of physics come from including virtual particles. So we know they're there, and we know, therefore, empty space is not so simple. Nothing is not what we thought it was before. Okay. Now, we're so proud of ourselves for being able to do that, we apply that to the universe. We say, well, let's try and calculate the energy of empty space. And we do. We come up not with the best calculation, but the worst calculation in all of physics. You can't see it, but there's a 1 there. We come up with the energy of empty space should be roughly a gazillion times the energy of everything we see. 120 orders of magnitude too large. We know that can't be the case because if the energy of empty space were that big, we just wouldn't be here. No galaxies would have ever formed. The universe would have been expanding so fast at early times that nothing would have happened. Literally nothing would have ever happened. So, and we knew, and this problem has been around since I've been a graduate student, and it's because it was the worst problem in physics, we never talked about it. But actually, we knew we could go to bed at night because we knew the answer. Theorists. We knew the answer had to be 0. It had to be 0, because first of all, 0 is a pretty number. And secondly, for another really subtle reason. If it weren't 0, then, and it would say it wasn't bigger than the energy of everything, all matter in the universe, we'd have to cancel this huge number to 120 decimal places, leaving something non-zero in the 121st decimal place. No one knows how to do that in science. But we can make 0 very easily with mathematical symmetries. We can have things that are equal and opposite and cancel exactly, so we figured there was some new symmetry of nature which would make everything simple and make the energy of empty space 0. Because this kind of fine-tuning is impossible to imagine, at least in particle physics. But maybe it's not impossible to imagine in astronomy, as I want to point out today, because of something that's happening right now. It's hard to imagine 2 large numbers that have nothing to do with one another, 2 large things, canceling almost exactly, but not exactly. It's almost impossible to imagine that happening, in fact. Except for right now. In fact, had it been sunny, my plan was to let all of you out right now and to go outside, because right now, as many of you know, there's an annular eclipse happening right now. If it were just sunny, we could see it, and I was going to insist that we all look at it. But what was that? It's who? Well, you can look directly at it. I was given, or people bought for me 3 pair of eclipse glasses, which were $1 yesterday, but if it were sunny, I'd be selling them for $10 now. But in any case, the point is, here it's an amazing thing. In fact, in many cases, it happens at this kind of year that they don't cancel exactly. They leave a little bit of a ring left over. But there's nothing that said the angular size of the moon and the sun had to be the same. There's no connection between them. It is truly an amazing accident that they're almost the same. And so the fact that we have these beautiful eclipses is an example that maybe unrelated things can sometimes cancel almost exactly and leave something small left over. And that's what we found is that our idea that they had to cancel exactly and be zero was wrong. What was pretty to us was wrong. And this was discovered about 10 years ago by the astronomers who didn't know what the hell they were doing. They were trying to measure this curve of the expansion rate of the universe using things called supernovae. And if I draw a straight line through this data set and bring it down here, what they were trying to do was measure how fast the universe is slowing down, which meant that these distant supernovae would fall along this curve. And they were shocked to discover that it fell above the straight line. It turns out several of us have predicted that, but no one listened. But I didn't believe it either, even though I predicted it. What happens is, if they fall above the straight line, naively it means the universe is actually accelerating. It's crazy. Except when you ask how much energy would you have to add into empty space to make the universe speed up like it is appearing to be speeding up, to fit that data, you have to put exactly what we're missing. If you put 70% of the energy of a flat universe in empty space, then everything works. Everything is in agreement with observation. We live in a flat universe. 30% of the energy of it is in dark matter. 70% of the energy of it is in empty space. We call it dark energy. We have no idea why it's there because when we try and calculate, we get the wrong answer. So we have not the slightest idea why it's there, but again, it makes you even more insignificant. Because now everything we see in the universe, everything in that nice, pretty picture I showed at the beginning, is really irrelevant. Because it's less than a 1% bit of cosmic pollution. In a universe dominated by dark matter and dark energy, if you got rid of us and the galaxy and all galaxies and everything that we can see with telescopes, you got rid of it all, the universe would be essentially the same. So truly, so much for a universe created for us. We are a bit of just pollution. We're irrelevant completely. That makes it more exciting. Oops. Oh, no, now I've got to go through this again. I pressed the button in the wrong direction, but it's so pretty. Okay. Let's do that. Okay. Boom. Okay. So, this is the picture of the universe we live in, and now I want to spend, I guess about 20 minutes left, the last 20 minutes talking about the consequences of this in terms of nothing. And I apologize for going a little long, but I tried to present this in a way I haven't done before with some wrinkles that people don't normally get to hear about. So I hope you at least appreciate that you now are in the fraternity. Anyway, but it's okay, don't worry about that. I don't want to. So anyway, the dominant energy universe resides in empty space. And as I said, we have no idea why it's there. And I stress that, no idea. I admit to not knowing, for those people who seem to think that I always write that we know everything. We don't know it. And in fact, as I point out, if anyone came here and lectured saying we knew it, did know it, they'd be lying, especially if they're string theorists. Now, what it makes it very exciting is that it is probably tied up to the very nature and origin of space, which is why we're so excited to find it there, because it means we don't understand how energy affects gravity at a quantum mechanical level. We don't understand that, and that's exciting. And as I say, it will also determine our future, and that's not so exciting, as I'll mention. It means we live in the worst of all possible universes to live in. So much for the universe made for us. Anyway, let me now tell you the real reason that physicists or theorists knew the universe was flat, we thought. Because one of the things we teach high school students, or at least in Canada they probably still teach high school students this, is if you take a ball or a coin and throw it up in the air, it comes back down, you throw it up faster, it takes longer to come back down, you throw it up really fast, it doesn't come down at all. And that we could calculate that very simply. Take you back to a wonderful time in your life, to high school physics class, and we can say that the energy of that ball has two pieces. A positive piece, we call it the kinetic energy, and a negative piece, we call it the potential energy. And it just becomes bookkeeping. If we throw that ball up fast enough so that the positive piece beats the negative piece, so the total energy is bigger than zero, the ball will escape. If the negative piece beats the positive piece, if the gravitational attraction beats the positive piece coming from the speed, the total energy is less than zero. And the coin or the ball will come back down. It's just bookkeeping. Now, what's amazing about the universe is it's exactly the same way. If the universe is the same everywhere, we thought we could determine the future of the universe by just thinking about what... See, if it's the same everywhere, then what happens to one galaxy will happen to all galaxies. So to figure if the universe is expanding forever, we don't have to do any fancy general relativity even. We just have to look at a region of galaxies. We're at the center. These are, as I point out, these are not sperm. These are galaxies. And we look at a galaxy at the edge of that region, and it's moving away from us because the universe is expanding. And the question is, will it come back? And the answer is high school physics. We calculate the positive piece of its energy, and that comes from its speed, which happens to come from the expansion rate of the universe, called the Hubble expansion. The negative piece comes from adding up the gravitational attraction of all the stuff in here, including dark matter. That's why we had to know dark matter. That's why I got involved. Because only if you include dark matter can you, we thought, get the right answer, and that gives you the negative piece. And if the positive piece beats the negative piece, that means if the negative piece beats the positive piece, so B over A is bigger than 1, then the total energy of this galaxy is negative, and it'll collapse in. If the positive piece beats the negative piece, so B over A is less than 1, then that galaxy will go on expanding forever. What is amazing is that actually this ratio is nothing other than this quantity omega, which is related to the curvature of the universe. And we now know omega is precisely 1. We live in a flat universe. But what does that mean? That means B is precisely equal to A. What does that mean? That means the negative piece is precisely equal to the positive piece. What does that mean? That means the total energy, gravitational energy of every object in the universe is precisely 0. Now, if you were creating a universe from nothing, what would you make the total gravitational energy of every object? That is telling, and that's one of the telling things that caused me to, in some ways, write the book I just did. Because if we're thinking about how you create a universe from nothing, it is a remarkable fact that the gravitational energy of every object in a universe that's not empty, but a universe full of stuff, can be 0. That defeats our intuition and our common sense. And the reason these two ignorant guys here the other night were saying you can't create something from nothing is because they don't understand things like that. The total energy of something can be 0. And that's a profoundly important fact. Okay. So now I want to spend the rest of the time talking about nothing. Well, maybe. Anyway. The first thing, and I had to do this in steps in the book at least, because nothing is such a non-intuitive concept that I think it's really important to talk about. I would argue, and I will refuse ever to back down on this point, that nothing is a physical quantity. It's not a philosophical quantity. Just like something is a physical quantity. So to understand physical quantities, we actually have to ask the universe. The universe tells us about physical quantities. We don't decide about them by a logic or some deep reflection. The universe tells us what nothing is. And I've shown you that nothing is more complicated than you thought. At least this kind of nothing. If you take nothing to be the nothing of the Bible, the nothing of which is an infinite, dark, empty void, empty space, which is a pretty good definition for most people of nothing. That kind of nothing is actually unstable. Because these quantum fluctuations that I talked about are occurring in that nothing all the time. And when you add gravity into the mix, the reason these particles pop in and out of existence, disappear quickly, is if they didn't, they would violate energy conservation. You create two particles, their mass has energy, mass is energy, and you can't. If it started out with 0 energy, you can't create real particles that have energy because you'd violate energy conservation. That's the argument people often use for why you can't create a universe from nothing. But if you add gravity in the mix, if the gravitational attraction of those particles is great enough, the negative energy that comes from their gravitational attraction can equal the positive energy that comes from their rest mass, and then they can exist with impunity. And you will be guaranteed in a universe governed by quantum mechanics that empty space will not remain empty for long. Quantum fluctuations will occur, and for long I mean if you're willing to wait a long, long time. Quantum fluctuations will occur, they must occur, and gravity will be such that some of those quantum fluctuations will produce pairs of particles that have 0 total energy, and those particles continue to exist. So if you wait long enough in empty space, it'll fill itself up. So one of the first answer to the question, why is there something rather than nothing, if your nothing is empty space, is that nothing is unstable. It would be a much more profound question to ask, why is there nothing rather than something? But you wouldn't ask the question if there were, because there would be nothing. But nothing can't exist easily on its own. The point is, it's not a natural state if your nothing is just empty space. Now, when I say that, some people, as the two people here might have talked about if they had the brains, but I don't think so. They'd say, well, that's not nothing, because that's space. Where did the space come from? And that's not that's a reasonable question. And let me stress what I said here, because I think it's really important. There's no contradiction for making real matter appear from nothing. You don't need magic, you don't need superstition, and you don't need any outside power to intervene. There's no need for some cosmic intelligence, which I agree with Matt. Why do you go from your worries about something for nothing to assume you had to have a cosmic intelligence? It's the same kind of nonsense that leads people to see something strange in the sky and say it's aliens. You know, it's not a balloon. It's not something. It had to be aliens, because it has to be an intelligence. We're hardwired to believe that kind of nonsense. And you don't need an intelligence to create matter from nothing. It happens naturally. Okay. But the second kind of nothing is, okay, what about empty space? Well, it turns out, remember, space and time in general relativity are dynamical quantities. Now, if you apply quantum mechanics to those dynamical quantities, and if you had a quantum theory of gravity, which I stress we don't have, but if you did, any quantum theory of gravity, space and time would be quantum objects. That means space and time would fluctuate at small scales. And that means you would create not just particles in empty space, but universes. You'd create space itself. And you'd create spaces that would pop in and out of existence in a time scale so short you couldn't measure them. You'd create spaces from where there was no spaces, and time from where there was no time, which is a much better definition of nothing, perhaps. It's not that I'm talking about vacuum fluctuations in our universe, as some people have argued. We don't even need a universe. Universes can come into existence spontaneously, but most of those universes, like most virtual particles, will pop in and out of existence in a time scale so short you can't see them. The only ones that can persist forever are universes that have zero total energy, because they don't violate any rules. Now, it would be oh so simple if everything fit together and I just said, look, a flat universe has zero total energy, and that's the universe we live in. That's not so simple. That's not the way it works, unfortunately. Because we can't even calculate the total energy of a flat universe. I told you that the gravitational energy of every object in a flat universe is zero, and that's true. But there's a lot more energy than just gravitational energy. There's rest mass energy. And we can't calculate it for a flat universe, which is in principle infinite. The only universe we can actually calculate the total energy of is a closed universe. And a closed universe, it turns out, has zero total energy. But we don't live in a closed universe. Well, most closed universes, as I pointed out, closed universes expand and collapse again if they're full of matter and nothing else. And therefore, most closed universes, it turns out that you create by quantum mechanics, will expand and contract in a time scale on the average of a millionth 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 of a billionth of a second. Too short for this lecture. So, we don't live in those universes. What kind of universe could live long enough for consciousness to arise by evolution and ask the question, why is there something rather than nothing? And it turns out the only kind of universe that could persist is one that for a while was dominated by the energy of empty space at early times. Now, it turns out the theories of particle physics that we have, a theory called inflation, predicts precisely that. That for a while, and just a short while, the energy of the universe was dominated by the energy of empty space. And the argument, which again I haven't presented before, is, since I'm in Canada, is based on beer. Some of you may have had a party and bought beer and forgot to put it in the fridge. Often it's happened to me. And so what do? You put it in the freezer. And then you forget about it. And then you open up the beer. You take it outside. It's okay. You open it up. And you open it up, and what happens? Boom, the beer suddenly freezes and the beer bottle breaks. Has that ever happened to anyone in this room? Yeah, okay, good, okay. We're in Canada, of course. What happened? Well, under high pressure, the beer is a liquid. When you let the top off, a phase transition happens, and the beer suddenly freezes in the process, releasing lots of energy. While it was a liquid and under high pressure, it was storing a lot of energy that it could release enough to break the bottle. As our theories of particle physics tell us that as the universe cooled, it's quite likely that it got stuck in a state, a so-called metastable state, where energy was briefly stored in empty space until a phase transition happened, just like in that beer bottle, and that energy was released. But during that short time, 10 to the minus 35 seconds, we think, according to our theories of particle physics, during that short time, that energy was stored, so much energy that it produced something like the energy we see now in empty space, causing the universe to accelerate very rapidly. And we can calculate that during 10 to the minus 35 seconds, it is quite possible for the universe to expand by a factor of 10 to the 90th. Taking a microscopically small closed universe that might have been created at the beginning of time and puffing it up to be so large that it would look flat today. Because just like when you blow a balloon up, it looks flat. When you take a closed universe and you puff it up, it looks flatter and flatter and flatter. So the inflation will force the universe to appear flatter. And if inflation didn't happen, the universe would have collapsed in a time of about 10 to the minus 35 seconds. So you can create closed universes from nothing, but the only closed universe that could survive long enough for life to evolve in it is one that essentially looks flat, just like the one we live in. So if you were going to ask, what is the characteristic of a universe that was created from nothing, and by nothing I don't mean just empty space, I mean no space, it would have the characteristics exactly equal to those we see. It would be flat, and by the way, inflation is that theory that predicts those fluctuations that agree identically with the picture I showed you, giving us great confidence that it actually happened. So everything is completely plausible and, in fact, suggestive. Our universe has the characteristics of a universe if that universe had been created from nothing by normal physical processes. Now, when I say that, that's not good enough. Because that universe was created from nothing without God. And for many people, the definition of nothing is that from which only God can create something. So that's not good enough because they say, look, you don't have particles, you don't have space, but you have the laws of physics. Well, even the laws of physics themselves may be accidental. Is it okay if I go on for 5 or 10 more minutes? Is that okay? Okay. Good. Well, good, because I'm going on for 2 hours. No, anyway. This is a discovery we've been driven to, and it's a discovery many of us don't like. I don't. If you ask me, I think it's awful, but it may be true. And the reason we've been driven to it is this cosmic coincidence that has driven people crazy. This is a brief history of time. This is the density of matter as the universe expands. It falls as 1 over the volume. The density of matter, as galaxies get further and further apart, that density goes down. This is the energy density of empty space. It remains constant because there's nothing to dilute. If what we have now measured is true, we live right here, at a time when the energy of empty space is about 2.5 times the energy of all matter in the universe. The problem with this picture is it's worrisome because this means we live at approximately the only time in the history of the universe when those two numbers are the same. At all earlier times, the energy density of matter was much bigger than the energy density of empty space. At all later times, the energy density of empty space is much bigger than that of matter. Why do we live 13.7 billion years at a special time? Copernicus told us it's not supposed to be that way. There's nothing special about 13.7 billion years. It's not a fundamental constant of nature in any way. Why should that coincidence happen now and at no other time? It almost sounds religious. So people have suggested the answer is the following. Galaxies exist. Why is that? Well, if I made the energy of empty space, say, 50 times bigger, then these two curves would cross not here, but there. But let's see what happens at this time. Well, this is the time when galaxies first formed. If the energy density of empty space had been bigger than the energy density of matter before galaxies have formed, galaxies wouldn't have formed. Because remember, the energy in empty space is gravitationally repulsive. If it had dominated over the energy of matter before galaxies formed, it would have pushed apart the matter before the galaxies couldn't have formed. And some people have suggested that's telling us something. And it's led to something I call anthropic mania. If there are many universes, and the energy of empty space can vary in each one, it's a random variable, then only in those universes in which not much greater than what we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is here because astronomers are here to observe it. That's why you're all here today. Now, it sounds ridiculous. It sounds almost religious. It sounds like this silly fine-tuning that these people seem to think about. It's not. It's just cosmic natural selection. We would be very surprised to find ourselves living in a universe in which we couldn't live. That would be worth talking about. It's just like bees and flowers, as I say. Bees can tell the colors of flowers not because they were designed to do that, but if they couldn't, they wouldn't survive. And if there are many different universes, then the one we expect to live in would be one in which the laws of nature were such that we could live in it. And here's one law of nature, the energy of empty space, that if it were much bigger, we couldn't live in. By the way, there's some fine-tuning in the sense that that number is very small compared to what we naively expected, but it's not fine-tuning. It could have been 0, and we could have lived just fine. In fact, the universe would be better if the energy of empty space were 0. So these guys who think that these things are fine-tuned for us are wrong. If God really cared about us, he would have made the energy of the universe 0, as I'll show you. Okay, but it certainly, if it varied much from what it was, we wouldn't be here. So that has led people to this idea that maybe this fundamental constant of nature is anthropic. It's related to our existence. Now, particle physicists have jumped on this because particle physicists are way ahead of cosmologists. Because cosmology is one number we don't understand, the energy of empty space. In particle physics, there's many more numbers we haven't understood for far longer. Okay? Why is gravity the weakest force in nature? Why is the proton 2,000 times heavier than the electron? Why are there 3 generations of elementary particles? These are the problems that I became a physicist to try and understand. But particle physicists, a number of them, have jumped on this and said, this is great. Maybe we don't have to understand anything. Maybe not just the energy of empty space, but maybe everything is an accident. Everything is an accident, randomly determined, and if there was any different, we wouldn't be here. Then we don't need a theory of everything, we need a theory of anything. And of course, some people think we have such a theory. It's called string theory. So this is my one cartoon. It's not as profound as the cartoons of Jesus and Mo, but it'll do. So one guy says to another, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. The second guy goes, okay, what would that imply? First guy goes, I don't know. So that's the story of string theory over the last 40 years. String theory was created and people thought it's a great idea. It'll tell us a theory of everything. It'll force the universe to be exactly what we see. But in fact, it has this problem. It has 10 dimensions or 11 dimensions in the theory. We only see 3 or 4, and you have to get rid of the others. Normally we think by compactifying them into small scales that you can't see if the theory were true, and we don't have any evidence that it is. But every different way you compactify those extra dimensions produces a different 4-dimensional universe. A different universe with 3 dimensions of space and 1 of time, where the laws of physics are different. So every wart in string theory becomes a beauty mark, because now they call this the landscape. Because if string theory were true, there'd be 10 to the 500 possible different universes, in every one of which the laws of physics would be different, but in one of which, at least, the laws of physics would be what we see. And the energy of empty space would be what we measure. Now, is this science? I don't know. Because if you have a theory that can predict anything, then anything you could measure would be consistent with the theory, and there's no way to falsify it. This is a problem. But it may be true. I mean, it may be a fundamental problem at the heart of physics. This may be true. It may be that the laws of physics are determined accidentally. But if they are, then the laws of physics come into existence when our universe comes into existence. And if that's the case, in my opinion, that is the last nail on the coffin of those people who need God. Because in that case, you create not just particles in space, not just the space, but the laws themselves. They all arise naturally from nothing. Now, what is this nothing? This nothing is actually, in some sense, many possible universes, some of which don't yet exist, some of which will exist tomorrow, something we call a multiverse. It could be that there are an infinite number of possible universes that could come into existence in an infinite region, some of which doesn't even exist because you create the space of that region as the universe becomes created. We call that a multiverse, and I want to point out that in some sense, philosophically, that multiverse fulfills the role of what these guys here needed for their God. Because it is the equivalent to what Aristotle might have called the prime mover, or the Catholic Church would call the first cause. Because the multiverse, they need something that lives outside of time. I'll pretend I'm them here. No, anyway, they live here outside of time, outside of space that might be eternal. And they say, oh, it's a God. But in fact, a multiverse could be just that. It could be eternal. It lives outside of our space and outside of our time. Now, when I've talked about this, and I've debated this to some Nudnik apologists, like Dinesh D'Souza and others, they say, you created this multiverse because you don't like God. Well, it's true I don't like God. But that's not the reason it's arisen in physics. It's arisen in physics because we've been driven to it by observing the universe. We don't even like it, some of us. I'd prefer fundamental laws that I could predict from first principles, and maybe that's the case. I don't know. But we've been driven to it by the universe. God didn't enter into the question at all, or the existence of anything. We just wanted to understand how the universe works. Okay. Last, happy to say, the last kind of nothing. And I do this, I'm only doing this in deference to my late dear friend Christopher Hitchens, who we all miss. And the world is a lesser place because he's gone. Christopher was writing the foreword for my book before he became too ill to complete it. And we used to talk a lot about science, anyway, we used to. And he illuminated many things for me about the world. And when I was telling him about this, he said, nothing is heading towards as fast as it can be. And what do you mean by this? You know what? I think because I've taken a little too long, I'm going to skip the details. It's a pity, but it's beautiful, but I'm going to skip it. No, I'm not going on too long. No, you can't convince me. I'll say it in words. I'll say some in words. The key word is that the rest of the universe is going to disappear before our very eyes. Because if the universe is dominated by the energy of empty space, then it's expanding faster and faster and faster. And distant galaxies are moving away from us faster and faster and faster. And eventually, they'll be moving away from us faster than the speed of light. That sounds like it shouldn't happen. Because we taught you in school that nothing travels faster than the speed of light, but we lied. You have to be like a lawyer and parse that a little more carefully. Nothing can travel through space faster than the speed of light, but space can do whatever the hell it wants. And space can carry objects away from us faster than light, and that's happening now. And as the universe speeds up, more and more galaxies will be carried away from us faster than light, and that means we won't see them. I was going to talk to you exactly about how they disappear, but it doesn't really matter. What it means is, in the far future, not on our planet, but a planet, let's say 100 billion years from now, or 1 trillion years from now, and there'll still be stars like our sun existing then. There'll be civilizations that evolve on organic materials or on stars. They'll develop scientists, and those scientists will discover the laws of physics. They'll build telescopes. They'll look out, and what will they see? They'll see the universe we thought we lived in 100 years ago. Because all galaxies other than our own will have disappeared. And 85 years ago, that's what science thought. Science thought the entire universe was our Milky Way galaxy, a single human lifetime ago. Put that in perspective. That's why we're just like the early map makers trying to understand the universe. It's not surprising that we're surprised all the time. In a single human lifetime, we've gone from one galaxy to 400 billion galaxies. But in the far future, they'll only be able to see one. And moreover, they'll even get a worse picture because they won't have any idea the Big Bang happened. And I will spend 2 or 3 minutes on this, which I don't normally talk about in public. every bit of evidence for the Big Bang will disappear. The Hubble expansion, the fact that universes are moving, or that galaxies are moving away from us, will go away because the galaxies will have gone away. The galaxies are tracers of the expansion. If we can't see other galaxies, we won't know the universe is expanding. The first bit of evidence for the Big Bang. What about the cosmic microwave background? That beautiful afterglow of the Big Bang. It's going to disappear. Because, in fact, here's a picture of it now. A Nobel Prize-winning picture, it turns out. It will go away. Because as the universe expands, that radiation will redshift. It'll get longer and longer frequency, and its intensity will go down. So when the universe is 100 billion years old, 10 times older than it is roughly now, then the intensity of that radiation will be down by a factor of 1,000,000 million. That means experimentalists will have to be 1,000,000 times smarter. Well, that's easy to expect, but it turns out that won't work because our galaxy has free electrons in it. And because it has free electrons, there's something called a plasma frequency, which you can calculate. And a plasma frequency says the radiation below a certain frequency can't permeate our galaxy. And that frequency happens to be a kilohertz. When the universe is 50 times its present age, all of that radiation will have redshifted below the plasma frequency, and it won't be able to get into our galaxy. So observers who even build a detector or don't know what the hell they're doing and look anyway won't see anything. No Hubble expansion, no cosmic microwave background. The last pillar of the Big Bang happens to be the fact that we can predict the abundance of light elements. This is my famous wallet card that I have in my back pocket when people tell me there wasn't a Big Bang. I show them this and I say, see, there was a Big Bang. But we can predict over 10 orders of magnitude the abundance of light elements, and we get the answer exactly right. One of the reasons we know there was a Big Bang, and one of the reasons we know how many protons and neutrons there are in the universe. But when the universe is 1 trillion years old, most of the helium in the universe, see now 24% of the universe at the beginning of time, 24% of the universe was helium. Stars have made about 4% of helium. But when the universe is 1 trillion years old, 60% of the universe will be helium. Stars could have made all of the helium that's observed in the universe. You don't need a Big Bang to make the helium or any of the other light elements. So even the Big Bang abundances won't point towards a Big Bang. And so observers in that future will see a single galaxy living in an eternal, dark, empty space that's not expanding, and they'll come up with the picture, the false picture of the universe that we had 100 years ago. It's poetic in a way. And it means that we're kind of lucky right now. And as I've often said, we're very lucky because we're living at the only time in the history of the universe when we could know we're living at a very special time. And that's facetious. Because maybe in the far future there'll be other observables we can't see today that we'll be able to see that will give us new insights. Or maybe in the past, if we've been smart enough to evolve 5 billion years earlier, there would have been things. We don't know. But in the future, they'll get it wrong. Okay. So falsifiable science will return people to the wrong picture of the universe, which is kind of interesting because it means you have to have kind of cosmic humility, which is, those two words don't go together very well for cosmologists. But we maybe should realize that we don't yet understand everything. And just because everything fits together with this cockamamie picture, maybe there are new things that will change that picture in the long run. So, to conclude, why is there something rather than nothing in that case, in that awful future, where everything else disappears? Eventually the stars in our galaxy will burn out, and our galaxy will become cold and dark, and the universe will become cold and dark and empty. And in that universe, the answer to the question, why is there something rather than nothing, is quite simply, just wait, there won't be for long. And to me, that may be the most important answer because it represents the cosmic conceit of humans. And it comes in biology as well as in physics. People assume that we are the pinnacle of evolution. Those idiots are saying, why aren't evolving? Or P.Z. Myers said, idiots who talk to him say, why aren't we evolving? It's true that they're not. But still, the point is, we assume we are the pinnacle of evolution. That was all here for us. When in fact, 99.9% of all species that ever lived aren't here. And the same will be true in the future. Similarly, we have this cosmic conceit that the universe was created for us, and it's always going to be the way we see it. It's not going to be that way in the future. We are an instant when the universe is the way it is, and we happen to be here now, but it's not going to be that way in the future. The universe is dynamical, and it wasn't created for us. So, I think I'm going to skip Einstein versus God, too, in spite of how beautiful that discussion is, and end, because I really now have overstayed my welcome. And some of you have to pee. Okay. Science has demonstrated that a universe from nothing is not only plausible, but likely. Those are two words, plausible and likely. They're scientific terms. That means we don't say it, we know it for certain. We say it's likely, and we say it's plausible. But even the plausibility of that is so amazing that I think we should share that more broadly, which is why I wrote a book about it. What we mean by something and nothing has completely changed. I made that bigger now. I have to make it big, so big that even philosophers can understand it. Sorry. Because those classical notions of nothing, out of nothing, nothing comes, implies some classical definition of nothing that may be interesting, but it's not the universe. Nothing in the universe means something very different than it did before, as I've tried to show you. And therefore, that question, why is there something rather than nothing, isn't even an interesting question. It's like the question, why are there 5 planets? Used to be fascinating and interesting to Kepler. And he thought it had something to do with the 5 Platonic solids, you know. And there's a profound reason. We now understand there aren't 5 planets, there are 9 planets. And there are 9 planets. Neil deGrasse Tyson be damned, there are 9 planets. The interesting question is, you know, how did planets form? And how did different solar systems happen? And the interesting question about the universe is not why is there something rather than nothing, but how? How did the universe evolve, and how can we find out? And those are the questions that science is addressing. So when I tell you that you are insignificant, and you are, and when I tell you that the future is miserable, and it is, you should come away from here feeling great. Because we are here at this weird accident, this cosmic instant. And we should, instead of being depressed about the future and the fact that we aren't not the most important things in the universe, we should be emboldened by that and realize that the meaning we make from our lives is the meaning we make from our lives. That we are here in this brief instant, in this brief moment of the sun, and we should enjoy that fact and make the most of it with our brains. Thank you very much.